Hello everyone. Today, my team and I are excited to present our AI-based chess piece color detection project for computer vision. My name is Pia Shumin, and my team members are Mia Usue, Teaka, and Tete-san. So let's dive into the details. So why did we choose this project? So chess is a game of precision, and AI-based chess engines rely on accurate board state recognition. Many existing systems use piece detection model, which can be quite computationally expensive and require complex training datasets. Our project aims to develop a system that can detect the colors of chess pieces black, white, or empty on a chessboard using image processing and machine learning techniques. Unlike conventional approaches, our method does not require complex object detection of detecting piece shapes, but instead rather focus on rather focuses on efficient game state recognition through color classification. So here's how it works. We assume that the initial positions of pieces are known. The AI then track color changes on the board to determine the current state. Since chess pieces are either black or white, we classify each square into three categories: black piece, white piece, empty square. This approach makes our system faster, more efficient, and computationally lightweight compared to traditional models. So, for the scope of our project, to ensure high accuracy, we defined three strict conditions for our project. Number one, color constraints. So, chess pieces are strictly black and white, no variations or different designs. The chessboard itself follows the standard black and white checkered pattern. Number two, camera and viewing conditions. The image is always captured from a top to down perspective, meaning we eliminate angle distortions and, and ensure consistent detection. The board size and positions are fixed, so this prevents errors caused by board displacement. And number three, lighting conditions. So chess piece detection heavily relies and depends on consistent lighting. Any shadow or uneven lighting could affect classification, so we maintained optimal illumination in our test environment. By keeping these factors fixed, we, ma- we maximize accuracy and minimize errors in our AI model. Objectives. With this setup, our project had four main objectives. First, to develop an AI-based system that detects black, white, and empty squares in the chessboard image. Second, to take advantage of known initial positions for tracking movements. Instead of detecting individual pieces every frame, we simply compare the new board state to the previous one, making it more efficient. Third, to ensure accurate classification under fixed lighting and camera conditions. Many vision-based chess systems fail when lighting changes, but our controlled setup helps maintain consistent accuracy. Lastly, to optimize the system for real-time or near real-time detection while keeping computational costs low. This means our model should be able to analyze an image in milliseconds, making it suitable for real-world chess applications. So these objectives guided our design choices and development workflow. So our setup. So this is how we set up our system to achieve the previous objectives. First, a stable and secure setup. Our chessboard is fixed in position to ensure the model always processes image from the same reference frame. This prevents misalignment issues that could interfere with accurate detection. Second, a top-down camera angle. By capturing the board from a direct overhead view, we eliminate perspective distortions. This helps maintain consistent square detection across images. Number three, optimize lighting conditions. Lighting is one of the biggest challenges in computer vision. Shadows, reflections, or variations in brightness can cause misclassification errors. We carefully adjusted the lighting to reduce inconsistencies, making the model more reliable. These factors created a controlled environment where our AI can perform efficiently and accurately. So with this setup in place, next is our data collection and model development.
For the dataset collection, we started by collecting raw images of the chessboard using a top-down camera setup. And initially, we captured 300 images of different board positions under varying conditions. However, 300 images were not sufficient for improving detection accuracy. Therefore, we expanded our dataset to 500 images, ensuring a diverse range of light conditions and board configurations. This finite dataset consists of 100 different chess piece positions, which serve as the foundation for training and optimizing our detection model. To detect the chessboard in our images, we use OpenCV's built-in function, cv2.find chessboard corners. This function identifies the intersection point of the chessboard squares, which are crucial for further processing. Once we successfully detected these corners, we apply a perspective transform to crop and align the board correctly. This step is essential because it ensures a uniform perspective across all images, reducing distortions and improving the accuracy of piece detection. While OpenCV's CV2.find chessboard corners provided a built-in method for detecting the chessboard, we face challenges in its practical application. One of the biggest issues was its inconsistency across different images. The detection process was significantly impacted by variations in lighting, shadows, reflections, and other environmental factors. Additionally, since we initially did not apply any image preprocessing techniques, the raw grayscale images led to poor detection results, making it difficult to process the both efficiently. In our first detection attempt, we directly applied CV2.find chessboard corners on grayscale images without any modifications. And as you can see, the results were poor. Out of 300 images, only 168 were successfully detected. To improve detection accuracy, we implemented image preprocessing techniques. We applied Gaussian blur to reduce noise and adaptive thresholding to improve contrast. These techniques help in making the chessboard patterns more recognizable. After implementing these improvements, our detection increased from 168 successful detections to 221 out of 300 images. After detecting the chessboard corners, we apply a perspective transform to normalize the board's appearance. This transformation corrects any distortions, ensuring that all images have a consistent viewpoint. And as a result, our detection became more stable and piece recognition accuracy improved. This step is crucial for building a reliable chess recognition system, as inconsistency in board alignment can cause errors in move detection. As part of our workflow, we also performed chessboard calibration to refine the accuracy of our board recognition. Calibration helps in adjusting by the camera lens, ensuring that the detected chessboard is as precise as possible. As you can see on the screen, our interface consists of three main patterns: start calibration, restart calibration, and start prediction. And also our system can also generate fan notation. When we click the Start button, the system takes just 1 second to analyze and calibrate the chessboard. It then provides a reset, ensuring all squares are correctly detected. And if we move the chessboard, we can recalibrate it by clicking the Restart calibration. And if there is an error occurs, we can simply click Restart calibration again, and it will reprocess the board and generate a corrected result.
So now um, we have calibrated the boat, and now we can get the boat image, the square image, and now we can get the each squares from the boat to make a model to train and then to use it on later. So this is the squares extraction from a boat image. You can see that there are squares here um, on the right side. Each the squares where the all the 64 squares where we extracted from this board image, and you can see there are types of squares. The squares where we each squares where we uh, describe as an empty squares or a piece occupied squares. Uh, and among the piece occupied square, there were black pits and white pits. So either the empty squares they can be the white or black empty squares, but it doesn't matter. Our model just need to distinguish between the empty squares and the piece occupying squares, and then black and white too. See, this is our initial workflow. At first, we wanted our model. We thought about training one model and make three outputs for each square of the boat. Uh, it it was taught as three apples, empty, white, and black. So to make it our initial approach, the each square for all 64 squares of above image, where we extracted the HOG feature. It is histogram oriented gradient features and make a data set. We wanted to make this because the HOG features are good for pattern recognition, and we thought it might be good enough for the empty and white and black squares to distinguish between to make a classification model between these squares. So, but we found that our data set, I mean, our data set is not large enough, so we needed to augment to make a bigger data set to make the image augmentation for that. And then we train the model. When we say the models, we use different models. We use SVN, random forest, and light GPN models, and we test each model on the NC and train new images and see how good these models are for this. And then let's see. So this is the image augmentation. This is the original image. This is the from the bulk calibration. We got this left side the big image, and when we make the image augmentation, you can see that the lighting and the textures change a little bit. Uh, they are three different, but we make like 10 or 20 more for the image augmentation, and then we train the model. Among the model, the light GPM model, which is the best between SVN, the random forest, and this is how it works for the NC and train new image. It is predicted. It's just one model pre-developed by every square. You can see that it is mostly correct, but not perfect. You can see this. There is some errors and identifying if a piece is a white or black. But you can see the model is not wrong about differentiating between the empty and the occupied squares. This is what we noticed choosing the HOG features, and it is not that good enough. It's not perfect to differentiate. It is a black or white piece, but it is good to differentiate the if a square is empty or if a square is occupied. So these are our observations. We needed image augmentations to be that good. And it takes long training time, approximately between 1 to 3 hours. And the light GPM model, it is with the highest accuracy, 98%. Um, the model is very good at distinguishing empty and occupied squares. It's 99% almost every time we check. It is good differentiate distinguishing the empty and occupied. But the model it has wrong predictions on distinguishing white and black pieces. Like it's like 1 to 4 wrong predictions, but above it is like around 94%. So, and when we test this model, when we do the live radiation, the frame rate is not that good. It is expensive in computational power. It takes a lot of CPU to predict if each square. So these are our observations on our initial workflow, which is just training one model to this with 3 outputs, empty, white, and black, and see this if it is good enough for the our observation. Okay, let's see. This is the final workflow. Um, it was good, but not perfect enough for to use for us. We wanted to make it better, so we make a new approach, which is this approach is to train two models instead of one model, and with two outputs for each model. One model is gonna predict if it is an occupied square or if it is an empty square. And the other model is gonna predict if a square is black or white piece in there. So basically, one model is gonna predict if it is a empty occupying, and if it is occupying, another model is gonna predict that occupied square is a empty is a black or white. So all each square for all 64 square about image. Oh, but this time we didn't need any augmentation. It is good enough. It was good enough, so we didn't do any image augmentation. One more is gonna extract the HOG features for pattern recognition, and the other more is gonna extract the HSV feature. It is hue, saturation, and value features for color detection. It is trained to predict occupy or empty square, and the model is another model is trained to predict if it is a black and white piece. And these two models combine together to get a full detection. It is the two-step prediction model. You can see here this is how the HOG model, histogram-oriented gradient, the pattern or recognition model predicting if it is an empty and occupied squares. It is correct in all squares. You can see the O means the occupied squares and the empty squares are not labeled here. This is the HSV model. It is predicting if it is a black or white pieces. You can see it is predicting all squares, so even if a piece is not there, it is still gonna predict if it is a white or black piece, and so it is predicting a white piece as white squares, a black piece as black squares. But you can also see even though a white piece is a black square, it is still predicted as a white, so it is correct for all of them. And even if a black piece is on a white square, it is still gonna be a black. And so these two models combine together a full prediction, combined prediction, HOG and HSV combined predictions, and you can see that it is 100% correct and everything is correct in here. This is our confusion metric, and the accuracy effort scores in here. It is kind of overfitting here, but it is good enough for us to apply in real, so we didn't try to improve for now, but we will try to improve for later uses, and we will discuss on the later parts. And this is our computer scores. Observations in here with the final tube stats prediction. The best thing, one of the best thing is that is no augmentation is needed. It takes shorter time to trade. It's only about 5 to 15 minutes. And random forest is the best in here with highest accuracy, 99%. And the model is both very good at distinguishing empty and occupied squares, not like the initial approach. And it is also good with white and dark pieces, 99% correct. The model has so far at most one or two predictions wrong or distinguishing white and black pieces. It could be wrong why they share rule and uneven light on both. We when we made the editor, we try to make the editor without any shadows or any uneven light, so it is kind of overfitting. It could be uh, predicting the shadows on the empty square as if there is occupied, something like that. And it is a low computational power, and it is faster frame rates even with two models predicting for light precision. So these are our first observations here.
Hello everyone. I'll be talking about our integration in WebApp for our project. As you can see in the image here, our web application mainly include both calibration, live piece color classification, and fine instructions of the buttons for the user interface. And I'll be explaining in depth in coming slides. I will walk you through the workflow between our backend and model, demonstrating how data flows between our system to deliver results in real time. Our project consists of three key steps. The first one is sending requests to the backend. The system starts by sending post requests to our backend, which is built using First API. These requests typically contain data such as images or post text that needs to be processed by our model. And the next thing is processing with First API and the model. First API acts as a bridge between the front end and our machine learning model. Once it receives the request, it forwards the data to our model, which then processes the input and return a response containing the necessary information. The last one is the displaying result in real time. Finally, the process results are displayed live, for example, as an overlay on the webcam feed or in fan notation for further analysis. This ensures real-time feedback and a seamless user experience. This structured workflow ensures efficient communication between the backend and the model, making it possible to analyze data quickly and display results without delays. So what is our difficulty in live view? The main thing is the live working becomes like so delayed and laggy as video streaming and fan prediction model are running at the same time. When we first use the light GPN like machine learning model, the live view was so delayed and laggy that we can't even use the prediction model because uh, like it delay for like around like 5 to 10 seconds, so it's not working like efficiently. So we changed to another the machine learning model, which use less computational power. So our current model work better, and like it's only like 1 like 2 seconds like delay. So it is, I might say, like it's acceptable. But we are still looking forward to improve the delay and the smooth of the video. The next thing is the user workflow of our system, highlighting like how different components interact to process and display prediction in real time. Our project begins with like starting the first API server, which acts as the backend for communication. Once the server is running, we render the web page or HTML and providing the like user-friendly interface. Next, we access and initialize the webcam, which allow us to capture a live view of the chatbot. Once the webcam feed is displayed, user can start calibration by clicking the Start Calibration button. This triggers a request to First API, and upon like successful calibration, the view is cropped to focus only on the chessboard. When user click Start Prediction, the system begins sending frames to the AI model. The model processes like each frame and return a response, which is displayed as an overlay on the live feed. This process continues like ensuring the frames and prediction are updated in real time. This structural flow ensures smooth and efficient experience, allowing the system to accurately track and analyze the chessboard continuously. I'll be showing you a video of the final result and the demo of our project. So let's see. As you can see here, I have initialized the first API server, and you can see the web application here. You can see the live view of the webcam that we connected here, and also the start calibration and start prediction button, and also the fan extraction. For now, like prediction is not working yet because I click the start calibration, and now you can only see the crop chessboard, the frame in the live view. And I'll be putting some like chess pieces on the board to start the prediction.
Start calibration.
Okay, so
Start prediction.
you can see that once I click the start prediction button, you can see the text overlay on the chessboard, the B for the black ones and the W for the white pieces. Okay. You can also see the fan notations here. It's also live and is updating every time I move a piece. Oh, sorry. Okay, let's show it again. And you can see the delay and the sound of the lagging like the video, but it's kind of acceptable. It's only like 1 or 2 seconds delay. You can see the live view here. Once I move the piece, like it immediately change and start the detection again and make a new like overlay text. But you can suddenly see like the due to the environment condition or the lighting condition, you can see it's like sometimes it kind of like show the pieces. Okay, so as we move forward with this project, our focus is on refining and like enhancing various aspects to improve accuracy, efficiency, and real-world adaptability. So let's get into our like future works. One of our primary goal is to compare previous and current box state accurately, track piece movements. This will help in detecting illegal moves, improving game logic, and ensuring precise state transition. We also aim to optimize live prediction performance by making it smoother and faster. Real-time processing is crucial for an interactive system like this, like our project. So reducing latency and the delay can enhance the user experience, and it will be more, how can I say, the ideal or optimal for the real world the applications. Then another key movement involves like reducing the overfitting in our machine learning model. Overfitting can lead to inaccurate prediction in different scenario, like to do the unseen data. So we are working on making our model more generalized and adaptable to various chessboard setups. So we need the larger data set and some of the images, the different stakes of images. And additionally, like, we want to improve the model like robustness in different lighting conditions and environments. As you can see in the video of our final result, you can see like due to the strong shadow or the strong lighting, it can sometimes how can I say that predict the mispredict the color due to the environmental factors. So like factors such as like shadow, glares, or like camera angles can affect detection accuracy. So enhancing adaptability will make the system more reliable in real-world application. Finally, like one of the more exciting future development is the full integration of the system with robotic. This will enable a robotic arm to not only recognize box sticks, but also physically move the chess pieces, creating a seamless and fully automated chess playing experience with a real person on the other side of the table. So a real person can play a chess model with a robot arm, with the like AI power, the AI powered like robot arm. With this improvement, our project will become more precise, efficient, and practical for real-world applications. Thank you so much, and that's all for our project. and thank you so much again for listening.